Algebra 2 lesson 5-5. Theorems about roots of polynomial equations. Now, if I have a polynomial equation, x to the third minus 5x squared minus 2x plus 24 not equal to 0. It has factors of x plus 2, x minus 3, x minus 4 equals 0. Just trust me on this issue. Which have negative 2, 3, and 4 as roots. Notice the product of 2, 3, and 4, 2 times 3 is 6, 6 times 4 is 24. That's the same as the constant term. Now let's consider this. Let's say 24x to the third minus 22x squared minus 5x plus 6. Its factors are x plus 1/2, x minus 2/3, and x minus 3/4, all equal to 0, which means it has roots of negative 1/2, 2/3, and 3/4. The numerators 1, 2, and 3 are all factors of the constant term 6, because 1 times 2 times 3 is 6. The denominators 2, 3, and 4 are all factors of the leading coefficient, 24. So, both the constant term and the leading coefficient of a polynomial can play a huge key role in identifying the rational roots of the related polynomial equation. This role is expressed in what we call the rational root theorem. Okay? The rational root theorem says this. If p of x equals a to the n, x to the n plus a to the n minus 1, x to the n minus 1 plus etc., 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 basically it's telling you if you have a number taken to a power and the power here is decreasing like x to the third, then x to the second, then x, and this the other power is going down as well. What you're going to have, if you have a polynomial with integer coefficients, positive and negative whole number coefficients, there are a limited number of possible roots of that particular equation. The integer roots must be a factor of a to the 0, or the leading coefficient. And the rational roots must have a reduced form, p over q, where p is an integer factor of a to the 0, and q is an integer factor of a to the n. Essentially what that means is this. If I have the equation 21x squared plus 29x plus 10 equals 0, okay, this will be here. The factors of the constant term are plus and minus 1, plus and minus 2, plus and minus 5, and plus and minus 10. And the factors of the leading coefficient are plus and minus 1, plus and minus 3, plus and minus 7, and plus and minus 21. If we actually could factor that, okay, I can, but you guys probably don't know how to factor it as well as I do. If I factor it, I could factor to x plus 2/3, x plus 5/7 equals 0, which means the roots are negative 2/3 and negative 5/7. If you'll notice, that comes from negative 2 over 3, 5 over 7. It comes from the factors of the constant term over the factors of the leading coefficient, which is what the rational root theorem is talking about. Okay, so if we need to find rational roots, if I'm trying to find the rational roots of x to the third plus x squared minus 3x minus 3 equals 0. Okay? The first thing I have to do is list all the possible rational roots. Okay? So if I'm going to list all the possible rational roots, I need to have factors of negative 3 divided by factors of 1. Okay? Because it's the constant term over the leading coefficient, and the coefficient in front of x to the third is 1. Okay? So I know all the factors of negative 3 are positive and negative 1, and positive and negative 3, because plus 1 times negative 3 gives me negative 3, and minus 1 times positive 3 gives me negative 3. Right? Now, all the factors of 1 are plus and minus 1. Okay? Plus 1 times plus 1 is positive 1. Negative 1 times negative 1 is positive 1. Okay? So, the possible rational roots are 1 divided by 1 is 1, so plus and minus 1, and plus and minus 3. Because if you have 1 in the denominator, it's really, really nice because you don't have to worry about any fractions. So my possible rational roots are plus and minus 1 and plus and minus 3. Now, to determine what the rational roots actually are, I have to test those roots. Right? I have to test every one of them. Okay? So I have to test, let's start with 1. Okay, my equation is x to the third plus x squared minus 3x minus 3. So I'm going to plug in 1 for x everywhere I see it. Okay, so I'm going to test 1. I'll put my colon after the 1. Okay, so I'm going to do 1 to the third plus 1 squared minus 3 times 1 minus 3. And I want to know, is that equal to 0? And this is 1 plus 1 minus 3 minus 3. That does not equal 0. Negative 4 does not equal 0. So that one doesn't work. So now I'm going to test negative 1. So I have negative 1 to the third plus negative 1 squared, make sure you put in the parentheses, minus 3 times negative 1 minus 3, does that equal 0? So I get negative 1 plus 1 plus 3 minus 3. So these two things cancel each other out, these two things cancel each other out, so that equals 0, so that works. So we now know that negative 1 is a 0. Okay, so we know negative 1 is a root. Let's test 3. Okay, so we're going to have 3 to the third plus 3 squared minus 3 times 3 minus 3. I can just look at that and tell you that's not going to equal 1. Okay, because if I do all that, that's going to be 27 plus 9 minus 9 minus 3. Okay, so these two cancel out. 27 minus 3 is 24. 24 does not equal 0. So that's not a root. So now I'm going to test negative 3. So I get negative 3 to the third plus negative 3 squared minus 3 times negative 3 minus 3. So that's negative 27 plus 9 plus 9 minus 3. Negative 27 plus 18. That's going to give me negative 12. That does not equal 0. So the only possible root, okay, the only rational root is negative 1. Okay, it would ask me to find the rational roots, rational numbers, not irrational numbers, like no square roots, no non-terminating decimals. So the only rational root of x to the third plus x squared minus 3x minus 3 is 1. Okay, so 1 is our only rational root here. So if we say 1 is my only rational root. Now let's look at number 2. Right? We want to find the possible rational roots for x to the third minus 4x squared minus 2x plus 8. Okay, so we need factors. Factors of 8 over factors of 1. So plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8, all over plus and minus 1. So basically, our possible factors, plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8. Okay? So we're going to find the rational roots of them. Okay? So we're just going to plug it into this problem all over again. So we're going to test all of them. So I'm going to test 1, so I'm going to have 1 cubed minus 4 times 1 squared minus 2 times 1 plus 8. Okay, so testing 1, that gives me I'm going to have 1 minus 4 minus 2 plus 8. So that's negative 3, negative 5 plus 8. Negative 5 plus negative 5 plus 8 is not equal to 0, so 1 doesn't. I'm going to test negative 1. So I get negative 1 cubed minus 4 times negative 1 minus 2 times negative 1 plus 8. This is a long and tedious process. Yes, I know that. And I'm very well aware of that. So it's negative 1 plus 4 plus 2 plus 8. I can look at that and that's not going to equal 0. So I'm going to move on. So now I can use 2. So 2. So I'm going to use 2 to the third minus. That's right. Right. 2 to the third. 2 to the third minus 4 times 2 squared minus 2 times 2 plus 8. So it's going to be 8 minus 16 plus 4 plus 8. This is going to cancel with note. That does not equal either. Sheesh. The more factors you have, the more annoying this gets. I'll just admit it. It gets very, very annoying. Okay, so now I'll check negative 2. So I'm going to have negative 2 to the third minus 4 times negative 2 squared minus 2 times negative 2 plus 8. So this is going to give me negative 8 Negative 2 squared is 4. 4 times 4 is negative 16. 2 times negative 2 is going to be positive 4 plus 8. Okay. This will cancel with this, but that does not equal 0, so I'm done there. What do we have? Plus or minus 2, plus or minus 4. Oh, we got to go plus or minus 4. Oh, let's go 4. Okay. So I'm going to go 4 cubed minus 4 times 4 squared minus 2 times 4 plus 8. 4 cubed is 64. 4 squared is 16 times 4 is 64 minus 64. Minus 8 plus 8. Hey, that one equals 0. Okay, that works. So we know 4 is a root. Now I can continue to keep testing all the rest of them. I can test negative 4, then I can test positive 8, and then I can test negative 8. Or I can look at this problem, okay, and I can say, okay, my original problem was x to the third plus x squared minus 3x minus 3. Okay. And we're trying to find the rational roots of this, right? It says to find the rational roots. So I'm going to find the rational roots, but I don't feel like multiplying out. I want to show you another way you can do it. I can continue testing to see which ones work and which ones don't. But now that I know that 4 works, I'm going to use 4 and I'm going to use synthetic division. So I'm going to say 4 divides into 1x to the third, 1x to the second, negative 3x, and negative 3. So 1 times 4 is 4, 4 plus 1 is 5, 5 times 4 is 20. Okay. Wait a second, I just read. No, I didn't write the problem down right. I didn't do that. Oh, a really hard time today. Go back to the original problem, which was x to the third, which is x to the third, minus 4x squared, I forgot that term, minus 2x plus 8. So this was my original problem. Okay? So we know that 4 is a factor, so 4 is going to go into 3, 2, 1, none, so it's going to go into 1, negative 4, negative 2, 8. So bring this down. 1 times 4 is 4, that's a 0, 0 times 4 is 0, that's negative 2, negative 2 times 4 is negative 8, so that's 0. So now I have x squared minus 2. Now I know that x squared minus 2 is going to give me an irrational number, because I'm going to have x squared equals 2, so x is going to equal plus or minus the square root of 2, which is irrational. I was told to find the rational roots. So the only rational root of this problem is 4. If I would have tested negative 4, positive 8, and negative 8, I would have found that they didn't work either. So I would have known I didn't have any more rational roots. Now that's a really long and complicated process, and I know it's tedious, but there's really no faster way around it than to actually do the math. Because even if your calculator can do it for you, some of them can and some of them cannot. I will force you to do the long way on your tests and quizzes, so you better do it on your homework. Once you find one root, you can use synthetic division like I just did to factor the polynomial. You can continue finding roots and dividing until you have a second degree polynomial, and then you can use the quadratic formula to find the remaining roots. Unless factor is much faster. So I want to find the roots of 2x to the third minus x squared plus 2x minus 1. Okay? So I need the factors of negative 1 divided by the factors of 2. So the factors of negative 1 are plus and minus 1. Factors of 2 are plus and minus 1, plus and minus 2. Okay. So my possible roots, not my definitive roots, my possible roots are plus and minus 1, plus and minus 1 half. Okay. I have 4 possible roots. Okay. So I'm going to test. I'm going to start with, let's start with 1. Okay. So if I start with 1, I'm going to test 1. I'm going to have 2 times 1 to the third minus 1 squared plus 2 times 1 minus 1. So 1 cubed is 1, 1 times 2 is 2, minus 1 plus 2 minus 1. Okay, that's basically 2 minus 1 is 1, 1 plus 2 is 3, 3 minus 1 is 2, and that's equal to 0. That is okay, let's test negative 1. Right? 2 times -1, 2 minus 1 squared, minus -1 squared, plus 2 times -1 minus 1. So -1 cubed is -1 times 2 is -2. -1 times is plus 1 minus 2 minus 1. So that's not equal to 0 either. So now we have to look at fractions. So let's try 1/2. Okay. If I test 1/2, I get 2 times 1/2 cubed minus 1/2 squared plus 2 times 1/2. We can put this in the calculator to see if it can minus 1 to see if it gives you 0. Okay. So 1/2 cubed is 1/8. 2 times 1/8 is 1/4. 1/4. 1/2 squared is 1/4 minus 1/4. 2 times 1/2 is 1 plus 1 minus 1. Hey, that equals 0. That works. So we now know that 1/2 is a root. Okay? So 1/2 is a root. Now that I know that, I'm going to use synthetic division at this point in time. Okay? So remember my original equation. Okay? My original equation, in case it's off the page, it's off the board here, is 2x to the third minus x squared plus 2x minus 1. So I know that 1/2 is a root, so I'm going to take 1/2 in here. Okay, 3, 2, 1, none, so let's do 2, -1, 2, -1. Bring this down. Half of 2 is 1. That's 0. 0 times 1/2 is 0. 2 times half of 2 is 1. So we know it had to end in 0. So it started with a cube. So now this is going to be 2x squared minus 2 equals 0. Okay. So now that I've gotten that far, okay, 2x squared plus 2, I can factor this. I'm going to take out the DCF first. So I'm going to take out a 2, and I'm going to be left with x squared minus 1. And x squared minus 1 factored to x plus 1 times x minus 1. So x equals -1 and positive 1. So my roots, wait. Plus 2. Man, I'm having a hard time. Sorry about that. It's plus 2, I missed my sign. So then when I take a 2 out, I get x squared plus 1 equals 0. So x squared equals -1. So x equals the square root of positive square root of -1. Well, -1 is I, so x is equal plus and minus I. So my roots then are 1/2 positive I and negative I. So those are all the roots of that figure. One of them is real, 2 of them are not, but that's all of the roots. Notice that the difference here is we're not looking for just the rational roots, we were looking for all of the roots. Okay, recall from lesson 4.8 when we talked about complex numbers, that the numbers a plus bi and a minus bi are conjugates. Similarly, the irrational numbers a plus the square root of b and a minus the square root of b are also conjugates. If a complex number or an irrational number is a root of a polynomial equation with rational coefficients, so then must its conjugate root. So basically that gives us a conjugate root theorem. Okay. If I have a root of a polynomial equation and that root happens to be an irrational number like a plus the square root of b, then its conjugate a minus the square root of b must also be a root. Okay. And if it's a plus bi is a root, then a minus bi must also be a root. So knowing that, okay, a cubic polynomial p of x has rational coefficients 2 plus 3i 2/3 are 2 roots. What is the additional root? Okay. We know that 2 plus 3i is a complex number. They have to come in pairs, like your socks and shoes. So it has to have its buddy with it. If 2 plus 3i is a root, then 2 minus 3i has to be the additional root. So the 3 roots of that cubic polynomial function are 2 plus 3i, 2 minus 3i, and 2/3. Okay. Now, let's use them. We're going to write a quartic polynomial function with rational coefficients that has the roots 1, 3, and 1 plus 2i. Okay. Well, if it has 1 plus 2i as a root, it also has 1 minus 2i is a root. These are fairly simple. Remember, we do the x minus 1, x minus 3. And now we're going to do this. We're going to do x. Okay, we know that x equals 1 plus 2i. So x, if we move everything over, minus 1 minus 2i is one of our factors. And if x equals 1 minus 2i, if we're going to move everything to the left-hand side, we're going to get x minus 1 plus 2i as our other factor. So those are our 4 factors of this polynomial function. In order to find the polynomial function, we have to multiply all 4 of those factors together. Yes, that seems very, very complicated, but it's actually not as bad as you think it is. This should factor fairly quickly. This would be x squared minus 3x minus x plus 3. So that factors to x squared minus 4x plus 3. By this time in your algebra career, you should be able to multiply those polynomials that quickly. If not, you need to practice that. Okay. Over here, I'm going to multiply x times x minus 1 plus 2i, negative 1 times x minus 1 plus 2i, and then negative 2i times x minus 1 plus 2i. I write that out because this one's a little bit harder. So this becomes x squared minus x plus 2i x minus x plus 1 minus 2i minus 2i x plus 2i minus 4i squared. And be very careful. If you skip this step here, you will most likely miss up the step right after it. Okay, so now that I'm looking out for like terms, I have an x squared. Okay, let's see here. Let's look at all my x's. I have a negative x here. I have a negative x here. Nothing else with just an x. That's minus 2x. I have a 2ix here and a negative 2ix here. Those go away. I have a negative 2i here and a positive 2i here. Those go away. I have a negative 4i squared, which is the same thing as saying plus 4 because I squared is negative 1. So I have 4 plus 1, which is 5. So I have x squared minus 2x plus 5. Let me see if I missed something. Oh, yeah. For that part of that equation. Okay. And so now I have to take these 2 parts of the equation and I have to multiply them together. You're like, oh, God, this is hard. It's not hard. It's just time consuming. Okay. So now I'm going to multiply x squared minus 4x plus 3 to x squared minus 2x plus 5. Okay. So I'm just going to put x squared minus 4x plus 3 right there. So when I multiply this, it's upside down. Work with it. Okay. I'm going to do x squared times x squared minus 4x plus 3 minus 2x times x squared minus 4x plus 3 plus 5 times x squared minus 4x plus 3. I write that out because most of you will need that. I don't, but most of you will. So x times x squared is x to the 4th. Here, x squared times x squared is x to the 4th. This is x to the 4th minus 4x to the 3rd plus 3x squared minus 2x to the 3rd plus 8x squared minus 6x. Notice the decimal sign is going to be moved after you. Plus 5x squared minus 20x plus 15. All right, now we've got to combine my terms. I only have one x to the 4th. Okay, so x to the 4th. I have a negative 4x to the 3rd and a negative 2x to the 3rd. That makes negative 6x to the 3rd. I have a 3x squared, an 8x squared, and a 5x squared. And they're all positive, so that's 16x squared. And then I have a negative 6x and a negative 20x is negative 26x, and a plus 15. So the final answer to this problem is what I'm going to highlight, but it's really hard to see otherwise. Right there. X to the 4th minus 6x to the 3rd plus 16x squared minus 26x plus 15. All right, the last thing we're going to do is look at Rene Descartes' rule of signs. The French mathematician René Descartes, who lived from 1596 to 1650, recognized the connection between the roots of a polynomial equation and the positive and negative signs in the standard form. So you have a polynomial with real coefficients written in standard form. The number of positive real roots is either equal to the number of sign changes between consecutive coefficients or is less than that by an even number. The number of negative real roots is either equal to the number of sign changes between consecutive coefficients of pure negative x or is less than that by an even number. In both cases, count multiple roots according to their multiplicity. Okay, what does that mean in people terms or in math terms? What does René Descartes' rule of signs tell us about the real roots of 2x to the fourth minus x to the third plus 3x squared minus 1 equals 0? Okay, we look at that. We look at p of x is exactly 2x to the fourth minus x to the third plus 3x squared minus 1. Okay? There's a sign change from here to here is one sign change. Okay? From here to here is another sign change, and from here to here is a third sign change. So there are 3 sign changes. Okay? In a positive one, so if there's 3 sign changes, okay, it says it's either equal to the number of sign changes or it's equal to 2 less than the number of sign changes because it's less than it by an even number. Okay, so less than that would be 2 less than this. So there's either 3 positive roots or 1 positive root. Okay, so from René Descartes' rule of signs, we can get there are either 3 positive roots or 1 positive root. Now we have to look at p of negative x. Okay. P of negative x just basically says every time you see an x, put in a negative. Okay. Well, when I take it to an even numbered exponent, it's not going to change that sign. It only changes the odd number of signs. So I would have 2x to the fourth plus x to the third, because a negative x to the third becomes a negative, and I'm going to have the opposite of x to the third. So that changes that sign, plus 3x squared minus 1. So let's take a look at the sign changes here. There's a sign change from here to here. That's the only sign change we have. So we have 1 sign change. So 1 sign change means we can have 1 or less than that by an even number. You can't have a negative number of roots. So there's 1 negative root. One possible negative root. Okay? So there is 1 possible negative root. That doesn't mean there is 1 negative root. It means that at most you can have 1 possible negative root. Okay? And this is a lot of stuff, and it's very tedious and time-consuming. It's not difficult, it's just tedious. The math that goes with this lesson is just flat out just boring and tedious, but it has to be done.